Hello and welcome. In today's session, we are going to dive deep into a fascinating and powerful type of NoSQL database, the column family model. This is a key concept in the world of big data, data science, and AI. So let's get started. All right, let's focus on our main topic, the column family model. So what exactly is a column family database? You might hear it called by a few different names, like a columnar database or a wide column store. Don't let the different names confuse you. They all refer to the same core idea. Essentially, these databases are a step up from the simple key value stores we've discussed before. They take the basic idea of a key pointing to a value, but they add more structure to that value part. As you can see on the screen, some of the biggest names in the tech world use this model. We have Apache Cassandra, Apache HBase, Google's Cloud Bigtable, and Amazon's DynamoDB. When you see companies like these using a technology, you know it's designed to solve very large-scale problems. To truly understand the power of a columnar database, we first need to remember how traditional databases work. Most databases you've probably used, like MySQL or PostgreSQL, are row-oriented. What does this mean? It means they store data row by row. Look at the simple table on the slide. We have two records. In a row-oriented database, all the information for row 1, John Smith and his address at AIT, is written together in one continuous block on the disk. Then all the information for row 2, Peter Parker, is written in the next block. This is very efficient when you need to write a new record or when you need to retrieve an entire record at once. Now, let's flip that idea on its head. Columnar databases, as the name suggests, organize data by field or by column. Look at the diagram. Instead of storing the entire first row together, the database stores all of the first name values together, John, Peter, and so on. Then it stores all of the last name values together, Smith, Parker, and finally, all of the address values are stored together. Why would we do this? This approach gives a massive performance advantage when you only need to read a few columns from a very large number of rows. Imagine you have a billion users and you just want to calculate the average age. A columnar database can just read the age column, ignoring all the other data, making the query incredibly fast. This is why systems like Apache Cassandra and Google's BigQuery are so powerful for analytics. So let's dig a little deeper into the why. As we said, traditional relational databases store data in rows. This is great for transactional systems where you're frequently adding or updating entire records, like a new user signing up or a customer placing an order. However, in the world of data analytics, our access patterns are very different. Think about it. How often do you need every single piece of information about a million users all at once? It's rare. More often, you need to look at specific attributes across those million users. For example, you might want to see the last login date and the country for all your users to analyze engagement. This is where the idea of column families comes in. We can group columns that are often read together into a family. By doing this, we tell the database to store these related columns physically close to each other on the disk. This optimizes our read access, making our analytical queries much faster. Let's look again at some of the popular column family databases. Apache Cassandra, for example, uses a concept called a key space, which is similar to a schema in a relational database. It's a container for your data. A key feature of these databases is that each column is treated as a separate item. This makes them efficient for aggregation queries. Queries like sum, count, average, minimum, and so on. Because all the values for a single column are stored together, the database can perform these calculations with minimal disk reading. This is why they are so widely used in data warehouses, for business intelligence, in customer relationship management systems, and even for library card catalogs, anywhere you need to analyze large datasets efficiently. Okay, let's break down the structure of these databases. It's like building with Legos. We start with the smallest pieces and build up from there. The most basic unit is the column. It's simple, just a name-value pair. For example, the name could be email and the value could be student@example.com.
Some implementations, like Cassandra, also add a timestamp to each column automatically. This is incredibly useful because it lets us know exactly when that piece of data was written, which helps in resolving conflicts. Now, we can group several of these columns together into what's called a supercolumn. A supercolumn is basically a named collection of columns. For instance, we could have a supercolumn named Address that contains columns for street, city, and postal code. Next, we group our columns into rows. Each row is identified by a unique row key. When a row contains only simple columns, we call this a column family. Think of it like a cable in a relational database, but much more flexible. And if a row contains supercolumns, we call it a supercolumn family. This gives us another level of nesting to organize our data. So the hierarchy is key space contains column families, which contain rows, which contain columns. It's this structure that gives us both flexibility and performance. Let's zoom in on a single row within a column family. First, we have the row key. This is the unique identifier for the entire row. It's how we look up our data. Then inside the row, we have our columns. Each column has three parts: name, the name of the attribute, like email address or age; value, the actual data for that attribute, like bob@example.com or 35; timestamp. This is the timestamp of when this specific piece of data was inserted or updated. This is crucial for versioning and conflict resolution, especially in distributed systems. Here's a great example of a column family called user profile. We have three rows identified by the row keys Bob, Brittany, and Tori. Now look closely. The row for Bob has columns for email address, gender, and age. The row for Brittany has the same columns, but the row for Tori is different. It has email address, country, and hair color. This is one of the most powerful features of a column family database. It's schemaless. Each row can have a different set of columns. You don't have to define a rigid table structure beforehand. This gives you flexibility to store diverse data. Now let's look at an example of a supercolumn family to see how it helps organize more complex data. Here, the row key is Billy Bragg, an artist. Inside this row, we have several supercolumns. One is named Personal Details, which contains columns for born and nationality. Another supercolumn is named Life's a Riot with Spy vs. Spy, which is an album title. It contains columns for the album's details. And a third supercolumn is Workers' Playtime, another album. Notice the column inside it for year with the value of 1988. This structure allows us to group related information together under a common key, making our data model for complex objects very clean and intuitive. When working with column families, you'll encounter two main types: static and dynamic. A static column family is closer to a traditional table. You can define a schema up front, specifying the column names and their data types. However, it's still flexible. Rows don't have to use all the defined columns. They can be sparse, meaning you only store the columns that actually have data for that row. A dynamic column family, on the other hand, has no predefined schema at all. Your application is completely free to add any column with any name at runtime. This offers maximum flexibility. This slide shows the difference visually. On the left, in the static column family, you can see a predictable table-like structure. The columns name, email, address, and state are defined. Even if a row like E. Gilmore doesn't have an address or state, the structure is known. On the right, in the dynamic column family, it's completely different. Each row key can have a completely different set of columns, and the application defines these on the fly. This is powerful, but requires the application to know how to interpret the data it reads. Finally, at the very top of our hierarchy, we have the key space. A key space is simply a container for all your column families. It's the equivalent of a database or a schema in the relational world. It's the outermost container that holds your entire application's data, which is then organized into various column families.
So let's quickly summarize the structure. At the top, we have the key space. Inside a key space, we have one or more column families. Inside a column family, we have rows, each identified by a unique row key. A row can contain columns, which are simple name-value pairs with a timestamp. Or, for more complex structures, a row can contain supercolumns, which are themselves collections of columns. Now that we understand the structure, let's revisit the core difference between row-oriented and column-oriented storage, as this is the most important concept. As we've discussed, most relational databases use a row store model, shown in diagram C. This is great for writing data, but in analytics, we often have scenarios where we write data once and read it many times. And during those reads, we typically only need a few columns from many rows. This is where column stores, shown in diagrams A and B, shine. They store all the values for a single column together. So if you want to calculate the average of the prod ID column, the database can read just that one block of data from the disk, making the operation extremely efficient. This is another great way to visualize it. On the left, the row-oriented database stores the entire first row, date, price, and size, then the entire second row, and so on. If you want to sum up all the prices, the database has to read all the data, date, price, and size, for every row, and then throw away the date and size information. That's a lot of wasted I/O. On the right, the column-oriented database stores all the dates together, then all the prices together, then all the sizes together. To sum the prices, it just reads the block of price data. It's much more efficient for this type of query. This table summarizes the trade-offs perfectly. For calculating an aggregate on a single column, like sum of price, the column-oriented database is very fast, while the row-oriented is slow. For compression, column-oriented is much better because storing similar data together allows for very effective compression algorithms. For retrieving just a few columns from a wide table, column-oriented is much faster. However, for inserting or updating a single new record, the row-oriented database is faster because it's just one write operation. And for retrieving a single complete record, row-oriented is also faster. The key takeaway is this: column-oriented databases are not designed for high-volume transaction data. They're designed for high-performance aggregate queries, which is exactly what you need in analytics and data warehousing. So to summarize the benefits, the biggest advantage of a column-oriented database is extremely fast data aggregation. If you need to summarize data from a single column across millions or billions of rows, this is the best tool for the job. This type of data is often called analytical data. It doesn't change frequently. You typically perform infrequent, large bulk writes, like dumping a day's worth of log data, and then you analyze it. The main limitation, or trade-off, is write performance. To write a single record to a columnar database, you have to write each field to its respective column store, which can be slower than a single write operation in a row store. Okay, let's now focus on one of the most popular column family databases, Apache Cassandra. On the slide, you can see links where you can try it out yourself. Cassandra is a column-oriented database that is famous for its scalability and high availability. It has a masterless architecture. This means there is no single master node that controls everything. Every node in the cluster is identical. This is fantastic because it means there's no single point of failure. If one node goes down, the database keeps running without any interruption. This architecture also allows for linear scale performance. This means if you double the number of nodes in your cluster, you double your throughput. You can scale out just by adding more machines. It also has automatic fault detection and recovery, a very flexible data model, and built-in data compression. And we interact with it using CQL, the Cassandra query language, which looks very similar to SQL.
Now, this is extremely important. When you start working with Cassandra, you must forget almost everything you know about relational database modeling. In the relational world, we design our tables around the entities and their relationships. We normalize our data. In Cassandra, we do the opposite. We design our data model around the queries we will run. You must think about what questions you will ask the database first, and then design your tables to answer those questions as efficiently as possible. To design our tables, we need to understand two key concepts in Cassandra: the partition key and the clustering column. The partition key has one primary job. It determines which node in the cluster your data will be stored on. When you write data, Cassandra calculates a hash of the partition key and uses that value to pick a node. When you query data, you must provide the partition key in your where clause so Cassandra knows exactly which node to go to. This is what makes reads so fast. It's used for where clauses and for grouping. The clustering column, on the other hand, determines the order in which the data is stored on disk within a partition. This is extremely useful for ordering your results. If you want to get the 10 most recent messages in a chat, you would use a clustering column to sort the messages by time. It's used for ordering your results. Let's look at an example. Here we create a table product by ID. The primary key is simply ID. In this case, ID is our partition key. When we want to retrieve a product, our where clause must specify the ID. The query select all from product by ID, where ID equals 1, is very efficient. Cassandra will hash the value of 1, immediately know which node holds that data, and go get it. Sometimes a single column isn't unique enough for our partition key. In that case, we can use a composite partition key. Look at the primary key definition here. Primary key, double parentheses, ID, comma, name. The double parentheses are important. They tell Cassandra that the combination of ID and name together forms the partition key. This means that when we query this table, we must provide a value for both ID and name in the where clause. A query with just ID will fail, as you see on the slide. The successful query provides both parts of the composite key, allowing Cassandra to find the exact partition where the data lives. Now let's bring in the clustering key. In this product by release year and size table, look at the primary key definition. Primary key, double parentheses, release year and size, comma, price. Here, release year and size is our composite partition key. This means all products with the same release year and size will be stored together on the same node. The second part, price, is our clustering key. This tells Cassandra that within the partition for a given year and size, the products should be sorted on disk by their price. So why is that useful? Because our data is pre-sorted on disk, we can run very efficient queries that involve ordering and ranges. For example, we can ask for the 50 most expensive products from 2019 of a certain size using order by price descending, limit 50. Cassandra doesn't have to sort the data on the fly. It just reads the data in the order it's already stored on disk. We can also run range queries on the clustering column, like asking for all products where the price is greater than $15. This is a very powerful feature for modeling time series data or any kind of data that needs to be sorted. Okay, let's formalize the rules for designing our data models in Cassandra. There are two fundamental rules you must always follow. Rule number 1, design your data model around your query patterns. Do not design it around your entities or relationships like you would in a relational database. Start with the questions you need to ask and build tables that answer those questions. Rule number 2, embrace denormalization. In the relational world, we try to avoid duplicating data. In Cassandra, we do it all the time. Why? Because Cassandra does not support joins. If you need data from two different things in one query, you must put that data together in a single table. Storage is cheap, but joins in a distributed system are expensive and complex. So we trade storage space for query performance.
Let's make this concrete with an example. Imagine we are building an e-commerce site called CS Mart. Our application has 4 query requirements. Q1, get a product by its ID. Q2, get a category by its ID. Q3, get all products that belong to a particular category. Q4, get all the categories that a particular product belongs to. Okay, let's design tables for the first 2 queries. For Q1, get a product by ID, this is easy. We create a table called product by ID. The primary key and our partition key is prod ID. This table is designed perfectly to answer this one specific question. For Q2, get a category by its ID. It's the same logic. We create a table category by ID, with cat ID as the primary key. These first 2 are straightforward. Now for Q3, get all products under a particular category. How do we solve this? We can't join our first 2 tables. So, following our design rules, we create a new table specifically for this query. We'll call it products by cat ID. Look at the primary key, cat ID, prod ID. Here, cat ID is the partition key, which means all products belonging to the same category will be stored together in one partition. Prod ID is the clustering key, which will sort the products within that category. Now our query select star from products by cat ID is where cat ID equals C001 is extremely efficient. Cassandra goes directly to the partition for C001 and reads all the products. Notice that we are duplicating product information here. That's denormalization, and it's the correct way to model in Cassandra. And finally, Q4, get the categories of a particular product. Again, we need a new table. We'll call it product cat by ID. The primary key is prod ID. To store the list of categories, we use one of Cassandra's special collection types, a set. A set is a collection of unique text values. So the category column can hold a list of all categories for that product. Now our query select category from product cat by ID, where prod ID equals P001, is simple and fast. So to satisfy our 4 query requirements, we created 4 separate tables. This is the essence of query-driven design in Cassandra. Now that we know how to model our data, let's look at the actual commands for manipulating data in Cassandra using CQL, the Cassandra query language. We'll cover 4 main areas. First, operations on key spaces. Second, operations on tables or column families. Third, the basic CRUD, create, read, update, and delete operations. And finally, we'll look at Cassandra's powerful collection types. If you're coming from a relational database background, this mapping is very helpful. A database in RDBMS is a key space in Cassandra. A table is a column family. A primary key is roughly equivalent to a partition key, although as we've seen, Cassandra's primary key can also include clustering columns. And columns and values are named the same in both worlds. Let's start with key spaces. To create a key space, we use the create key space command. The most important property here is replication. This tells Cassandra how many copies of the data to keep in the cluster. For example, a replication factor of 3 means there will be 3 copies of every piece of data, stored on 3 different nodes. This is how Cassandra achieves high availability. We can also drop a key space to delete it or alter a key space to change its properties. Here are the actual commands you would type into CQLS, the Cassandra command line shell. You can see the create key space command, where we name it test key space and set the replication strategy. Simple strategy is used for single data centers. We've set the replication factor to 1, which is only appropriate for a single node test setup. You can then describe key spaces to see all the key spaces in your cluster, use a key space to switch into it, and drop a key space to delete it.
Once we have a key space, we can create tables inside it. The create table syntax looks very familiar, just like SQL. We define our columns and their data types, and most importantly, we define the primary key. We can use describe tables to see all tables in the current key space, and describe table EMP to see the structure of a specific table. We can also alter table to add or drop columns, and of course, drop table to delete a table. A few more useful table operations. Truncate table is a very fast way to delete all the data in a table without deleting the table itself. And just like in relational databases, we can create an index. In Cassandra, this is called a secondary index. You create it on a column that is not part of the primary key. This allows you to query that column in your where clause. However, you should use secondary indexes carefully, as they have performance implications. It's usually better to design a new table for your query if possible. All right, let's look at the basic CRUD operations. First, we create our emp table. Then, to create data, we use the insert into command. The syntax is almost identical to SQL. We specify the table, the columns, and the values we want to insert. To update data, we use the update command. The important thing to note here is that the where clause must specify the full primary key of the row you want to update. You can't do a broad update like update all employees in Bangkok. You must identify the exact row. Interestingly, in Cassandra, update and insert are almost the same operation internally. If you update a row that doesn't exist, Cassandra will create it. This is called an upsert. To delete data, we use the delete command. Again, the where clause must specify the full primary key of the row you want to delete. To read data, we use the select statement. A select all will get all the data. A select with a where clause on the primary key, like emp id equals 1, is very efficient. Now, what if we want to query a column that is not the primary key, like emp sal? If you try to do this, Cassandra will give you an error. It forces you to query your data efficiently. The solution is to create a secondary index on that column, as shown. Once the index is created, the query on emp sal will succeed. Again, use this feature with caution, as they have performance implications. It's usually better to design a new table for your query if possible. So, to recap filtering. All filtering in Cassandra is done using the where clause. You can always query by the partition key. You can also perform range queries on your clustering columns. And if you've created one, you can query a secondary indexed column. The where clause supports several operators including equals, greater than, less than, in, contains, and contains key, which are used for querying collection types. Aggregation is a key use case for Cassandra. The data is naturally grouped by the partition key, and then sorted by the clustering columns. Designing your primary key correctly is critical for getting good performance on both reads and writes. Cassandra has built-in aggregate functions that you're already familiar with: count, min, max, sum, and average.
To perform aggregations effectively, we need to design our table with aggregation in mind. Here, we've created a new table, emp_ag. Look at the primary key. Primary key with emp_city, emp_sal, and emp_id. The partition key is emp_city. This means all employees from the same city will be stored together. This is our grouping key. The clustering columns are emp_sal and emp_id, which means that within each city, employees will be sorted first by salary in descending order and then by their ID in ascending order. This is our ordering key. We then insert the employee data into our new aggregate table. Now, because we designed our table with emp_city as the partition key, we can easily run group by queries on it. We can select count star and group by emp_city to see how many employees are in each city. We can also find the max of emp_sal for each city. Because the data is already sorted by salary within each partition, this is a very fast operation for Cassandra. Similarly, we can calculate the sum of salaries per city and the average salary per city. By designing our table around the aggregation query we wanted to perform, we make these calculations simple and efficient. One last powerful feature to cover is Cassandra's collection types. There are 3 types: set, list, and map. These allow you to store multiple values within a single column. First, let's look at set. A set is a collection of unique, sorted values. It's perfect for things like tags, or in this case, a list of email addresses for a student, where each email should only appear once. We define the column email with the type setText. As you can see in the example data, the student Joe has 2 unique email addresses stored in his email set.
Working with sets is easy. When you insert data, you provide the values inside curly braces. To update a set, you don't have to read it first. You can just tell Cassandra to add or remove elements. To add a new email, we use set email equals email plus new email. To remove an email, we use set email equals email minus old email. This is very efficient. Next, we have list. A list is a collection of non-unique values, and it preserves the order in which you insert them. This would be good for storing a list of a student's enrolled courses, where the order might matter, and a student could potentially enroll in the same course twice in different semesters. Here, we alter our table to add a new column, enrolled courses, with the type list of text. To update a list is similar to updating a set, but you use square brackets. You can append new items to the end of the list using the plus operator. You can also remove items from the list using the minus operator. Cassandra will remove all occurrences of the value you specify. Finally, we have map. A map is a collection of key value pairs. This is just like a dictionary or a hash map in a programming language. It's perfect for storing structured but flexible data, like an address, where you have keys like room no, dorm, and so on. Here, we alter the table to add an address column of type map of text. To update the map, we can add new key value pairs using the plus operator. We can also update the value for a specific key using the square bracket syntax, just like in Python or Java. And we can remove a key value pair from the map using the minus operator on the key. These collection types give you a lot of power and flexibility in your data modeling.